So welcome, everybody. Today we're going to be a little more relaxed in how we do things in terms of how far we get into the physics. So we're going to try to broaden our thinking about this. The easiest way to broaden your thinking when you want to move away from the physics is to focus on the mathematics. At least that's the way I tend to think of things. Allows you to cover a much broader range of systems to think about. So let me go ahead and start by sharing my screen here. Today, we are going to talk about shocks in a much more extended set of problems. So we think of it mostly in terms of society and history. And we're going to focus really on the questions of collapse and resilience and how those relate to shocks. I want to start, as usual, with a poem. So this is the poem by Percy, Shelley, who died extraordinarily young. He was only 30 years old when he passed away. It's called Ozymandias of Egypt. So let me just read it out. I met a traveler from an antique land who said, "Two vast and frontless legs of stone stand in the desert. Near them on the sand, half sunk or shattered by such lies, whose frown and wrinkled lip and sneer of cold command tell that its sculptor weld his passion thread, which yet survive, stamped on these lifeless things, the hand that mocked them and the heart that fed." And on the pedestal, these words appear. "My name is Ozymandias, king of kings. Look on my works, ye mighty, and despair. Nothing beside remains. Round the decay of that colossal wreck, boundless and bare, the lone and level sands stretch far away." This is a classical poem, really focused on the idea that you walk around the world and you see the ruins of civilizations from ages past. We're going to think a little bit about that as we go through the hour or so. Let me start by recalling things for you, trying to encapsulate the first three sessions in a really short format. So we're thinking about shocks. And if you remember, the shocks are essentially described in terms of a jump and a wave. Typically, shocks are caused by extreme events or instability. So the jump is propagating at some wave speed, and that's our shock. We started out in the second class by looking at planetary impact, really a bunch of extreme events. They caused impact craters, disruption, very large-scale systems there, spatially large-scale. In the third class, we looked at instability-driven shocks, which were typically at the human scale. Brain injuries, crash, typically some kind of an instability that resulted in a shock. All right, so that's what we've done so far. So we saw the blast injury case, for instance. Today, what we're going to do is to think about the same problem, but we're going to think about large-scale shocks in the human world. So not a single human anymore, but large collections of humans. To do this, we're going to have to rescale our thinking in terms of shocks. So I'll think of this as rescaling shocks themselves. So essentially redefine shocks in our heads so that we can see how this changes at larger scales. So let's talk about scales a little bit. Some of this is a quick recap, and some of this will tie to where we're going. So the first question is, when do you get a shock? And this picture on the left gives you an idea of that. So whatever system you have, you apply a certain force, you get some response. If to get a larger response, you have to apply a much higher force, that's the red curve, those kinds of systems will generate shocks. If, on the other hand, at some point to generate a larger response, you need a weaker force, or at least not as large of an increase in the force, so the force does not increase proportionately or linearly, then you will not get a shock. Instead, whatever disturbance you get spreads out and dissipates over time. Now, there's a short window of response and force over which those two overlap. We think of that as the linear domain. During that domain, the force and the response are proportional to each other. But think of that as sort of a limit. Once you pass a certain limit in the force, then you begin to either get a shock or you begin to get things spreading out. We're only interested in the red when you get a shock. And what you see in terms of the shock itself, if you look, for instance, as the pressure as a function of time, or if you think of the pressure as the force density as a function of time, initially everything is quiet, then at some time the shock arrives, and then the pressure jumps to a high level, so the force jumps to a high level. And then this jump itself propagates through space and time. So this is how we think about shocks. The question, though, is what's really happening in terms of this jump? So if I look in sufficiently closely, even at the shocks we've looked at before, let's say the shock wave that was going in the air when there was a blast, right? The shock wave that went from the blast. Even in those, if you go look at it closely, what you see is this. The pressure actually rises over some time. That time you're calling tau, it's the rise time of your shock wave here. If that rise time tau is much smaller than the time you can perceive, you think it's a jump, and you call it a shock. Okay? By the same token, if the pressure, that is the force that you apply, is much higher than this domain where both the red and the green curves are touching each other, you'll think it's a shock. So let's restate this. You're going to see something as a shock if the amplitude of the jump, how big the jump is larger than the force you can easily handle. So the forces you typically think about. If the jump is bigger than that, you're going to perceive it as a shock. And then the rise time, the rate at which this thing is rising, is much shorter than the time that you can perceive. Again, as far as you're concerned, it's a jump, and you will see it as a shock. So what you call a shock is really scaled by your capacity to respond, this pressure P0, the initial pressure below which you always understand what's going on, and the time it takes for you to respond, T0, the time it takes for you to see that something different has happened. If the shock jumps faster than T0, you'll see it as a shock. If the shock jumps larger than P0, you'll see it as a shock. We call this capacity to respond the capacity P0 and the response time T0. So what are those times? What are those responses? Let's just do an example here. So if you were to take your pressure time plot and rescale the plot, so you divide your time axis by T0 and your pressure axis by P0 and then replot the system, you'll see something like this. And then you call it a shock. So basically there's a characteristic pressure and a characteristic time, or a characteristic force and a characteristic time, above which, so if the pressure is above that, the force is above that, you'll see a shock. If your rise time is below the characteristic time, you'll see a shock. Okay. So let's take some examples. The two examples we looked at so far, we had the planetary impact problem. Remember, we hit a piece of rock. In that case, this capacity, P0, is on the order of 10 GPa. Gigapascals is simply a measure of the stress. The response time in that case is about 10 microseconds. Anything faster than 10 microseconds, you'll see as a shock. In the biological impact case, the wave in your brain, the capacity is only about 100 megapascals. It's much smaller than the case of the planetary impact because your brain tissue is much softer. And the response time, though, stays about the same. It's still 10 microseconds. You can't perceive anything at less than 10 microseconds anyway, so you see it as a shock. So that's the mechanical case. For every mechanical problem, we can find these kinds of scales. So if you're thinking about doing mining and you have a mine explosion, you can characterize these scales as well. But not all things that we are interested in are going to be mechanical. So there's my picture of the wave propagating inside your brain, right? As a consequence of a rotation. But now we want to rethink our problem in the case of non-mechanical shocks. So I'll give you an example that you guys are all very, very familiar with. So this is a traffic report. This is ABC2 News, our own local channel here. I've forgotten the date that this was, sometime recently. And I'm presuming that sound is going to run. Let's see.
Traffic story of the morning on the outer loop of 695 as you approach Bel Air Road. Here's a live look at the scene from our ABC2 News Wrangler. You can see right there on the right-hand side. We have a tractor trailer.
Okay, let me stop there and get you to think for a minute about traffic. So you're driving along on the highway. You see a car in front of you. That car is some distance away. You're moving at a certain speed, right? If you take the distance that car is away, divided by your speed, you get a time. That's the time, the response time of the system before you crash. That's one time scale in the system, one of those T0s. There's another time in the system, though, which is the speed at which you can react, your response time. So your human response time is determined by how old you are and how much experience you've got, and whether you had your cup of coffee in the morning, whether you're tired at night, whether did you go out on St. Patrick's Day and you're just coming home after having a lot to drink. Your response time has changed. That's also a scaling time. If the events in your traffic flow happen faster than any of the two times that I just talked about, you're going to perceive it as a shock. This is what you're seeing. Cars spaced a certain distance apart. Now, one thing to remember is this is a lot of people. It's a lot of different drivers, a lot of different distances between cars, approximately the same speed, a lot of different response times. Now, let's say one of those cars out there does something strange. So this lady's looking at a text message at the same time as she's driving, all right? And she swerves a little bit. The person behind her sees her swerving and begins to brake. The information that that person began to brake, the person behind him sees the brake light and begins to react, begins to respond. The response times of the human are now engaged in the traffic flow. And what you'll see is that information that that first person decided to put his foot on the brakes now propagates back through the stream of the cars. This is a wave propagation plot. And depending on those response times, you can develop a shock. So here's a simulation of that process. There are the cars down there. This is the density of cars that you're plotting here, and you develop a shock wave. This is a problem you can track. It's actually done fairly extensively in the transportation industry. You develop propagating shocks. This is the reason why sometimes you're driving along, suddenly everything seems to slow down, and then after a while, everything speeds up again. You can't see any reason why that happened. This is why it happens. Response times and your reaction to those response times. Okay, when one event happens, in this case, a stochastic event, right? Something that happened at random, a sudden, a chance event, that then triggers a shock wave inside your system. One of the cool things here, by the way, if you look at the top, this is a group from Georgia Tech that runs this calculation. You can go in and run your own calculation there, even though it's hosted on the MIT website. They call this thing a jammeton. This comes after, it's a pun on the word soliton that we use for solitary waves propagating through systems. So you can see this. You can actually do these kinds of experiments, and people do. But you guys are running the experiment every day when you go in. You should ask yourselves whether you're more likely to have a traffic jam the night of St. Patrick's Day or the morning after. And you can actually go back and look at the data and see what that tells you. So here's an example of a non-mechanical shock. You see what the response times were there. That was a very short response time, a very short time scale. So your T0 was really, really small. But we have other problems that are of interest to us that have very, very long time scales, at least by way of the individual human response. So here's a classic painting. This is by Thomas Cole. So he has a series of paintings about the Roman Empire. This is the one called Destruction, the collapse of the Roman Empire. And of course, this is an imaginary view of the collapse of the Roman Empire by the artist. So he sees the buildings collapsing, tidal waves coming in, the bridges, the viaducts, all of these are collapsing. I've forgotten what the bridges were called in Roman times, and then people falling off. Essentially, the collapse viewed in terms of all of the parts of the collapse of the civilization. So this is an example that you might see at very long time scales, right? So if you actually look at the collapse of the Roman Empire, it doesn't happen in a microsecond. It doesn't happen in 10 microseconds. It doesn't happen in seconds. It happens in fractions of a generation, maybe a couple of generations. The timescale changes. Now you can try to model these kinds of things, and people do, right? It turns out to be a really significant cottage industry at this point in terms of trying to model this. My interest here is mostly in the mathematical approach to this, and that's kind of interesting. If you want to take mathematics and try to model societies, this turns out to be a really tricky business, but a really interesting business. And you can learn a lot from it, even though you should take it as a given that your models are bad. Now, of course, there are those who say all models are bad, but some are useful, right? This is certainly the approach to take here. So I want to think a little bit about modeling things at very different timescales. Fundamentally, the way we're going to think about the problem is just changing the timescale. Turns out, because we change the timescale, we will have to change the length scale. We'll have to bring those two things together. All right. Now, of course, what you're doing here is trying to take science and mathematics and apply it to a human structure, a human organized structure, a social structure. So let's talk for a little bit about science. and what we can do with it and what we can't, right? So this is Galileo Galilei. It's a painting in the Uffizi Gallery. So those of you who've been to Florence, you've probably seen it. The painting itself is from, I don't know, about 50, 70 years after Galileo died. But let's assume it's a reasonable characteristic of the man. So let's go back and think about why we use science. One fundamental reason is it because it gives you a logical framework, a framework that you can use to define the world in your head. Essentially, for those of us who are scientists, it's a model, but it tells you how to build the world in your head. Now, there's a particular reason, though, that science has become really successful, is because it is founded in observations. So you look at the world and you see, this is what it is, you have the data. That's why you trust the science, because it's founded in observations. Because the reason you use the science is because it's founded in observations, but you're able to then say something about the future, right? You've got some predictive power. This is why you like science. So why you trust it and why you like it, or why you use it, these are different things. One is the observation, the other is the power. And most important, you like it because it is repeatable and testable. So you can do Galileo's experiment, I can do Galileo's experiment, and Newton could do Galileo's experiment. And compare the results, and you get the same results. That tells you you have some confidence in the particular hypothesis that you put forward, or the particular theory you put forward. So, observations, predictive power, and being repeatable and testable. Let's just think about this for a minute. Observations, going back to this problem with civilizations and societies and much larger scale things. Observations, maybe we have. Predictive power, this is really difficult to test. So you come up with a hypothesis, you may not have enough time as an individual to test your hypothesis. Repeatability, do you have enough data? Can you repeat an experiment? These are extremely difficult things. So it's hard to do science in this context. But fundamentally what you do is you take your observational data, you couple it to some physical principles, and you build a model. And you describe the model using mathematics. That's what most of us do as scientists, right? These days, we don't just use mathematics, we sometimes use computation. We generate data using computation, and then we use that to build some of our models. And we can argue extensively about whether that's a reasonable thing to do or not. We do it. We actually, a lot of the things that you are currently using in your world are the consequence of doing things through the computation. All right. So we have these models from science. We want to apply them to large scale. We've got to recognize, though, that there are two kinds of models we typically use. There are these deterministic models, where you believe that if you have a certain problem and you run through a process, you will always get one answer. And there are the stochastic models, which say that you have some distribution of inputs and you're going to get a distribution of outputs, and you have some statistical or probabilistic version of what's going to happen. So you don't say this is exactly what will happen, you say this is probably what will happen. And you can relate that to a bunch of ideas like entropy and chaos and so forth. And we don't have the time to walk through all of that. The reason I'm bringing it up is because this tension between these two kinds of models is a really important part of how you think about shocks in this larger scale problem. I want to start by showing you a real triumph of deterministic model. So this is a movie from the European Space Agency talking about the Rosetta mission to a comet. And let me just play this for a minute. The Rosetta mission was a mission launched to a comet. It went for 10 years through space. So it was launched in 2004 from Earth, right? That's the white line is the orbit of the satellite, the probe. A year later, it gets a gravity assist. So the Earth speeds it up, moves up, moves a little further away, and then gets a gravity assist from Mars. So it gets close to Mars and gets kicked faster again, moves up, catches up with Earth, gets another gravity assist, moves up, goes way outside the orbit of Mars, flies by an asteroid as it happens, keeps going. A third gravity assist, so you're 3 times you've run around the sun. 4 times, actually. Fly by another asteroid. This was all planned, by the way, just so we understand this process here. Then it goes to sleep in 2011. It wakes up, the probe wakes up 3 years later, and now has arrived at a comet. This is comet 67P Churyumov-Gerasimenko. The probe is now at the comet, begins to orbit the comet, stays with the comet, begins to map the surface of the comet, and eventually actually lands on the comet. Okay, the lander was called Philae. Now, I want you to just think about this. You've been in flight for 12 years. You went past one planet 3 times, the Earth. You went past Mars, and you used all of that to reach a comet, which is plummeting towards the sun. That is a triumph of deterministic modeling. That's why the models work, right? This is predictive power. I knew 12 years ago where the comet is going to be. And I could tell that if I launched it just this way, from just this one place, and used the little fins I have on the probe to move it just this much, I would get to that comet. And I would land on it. So this is, to give you the example, this was like taking a mosquito and landing it on a plummeting falcon. That's what you're doing. That's the difference in size scales. And by the way, the falcon is in Japan, and you're here. And you control the mosquito from here and land it there. That's what we do. So science works. The deterministic model does work. You can really go very, very far with that system. And when you get there, this is what you see. I had to show you these pictures. So this is the comet itself. It's actually 2 little lobes of material that are stuck together. You can see lots of craters on it. And if you get close enough, you can see the surface of the comet here. You can see the dust on the comet. And I want to point out something. Let's see if I can get my annotation. Here is the mouse. I guess this works. Down here where my cursor is, look at that boulder. Do you see the trail here? This boulder rolled down the hill on this comet. And this comet has negligible gravity, and yet the boulder is rolling down the hill. And you can track how it rolled. You can see where the boulder hit every time, how often it rolled, and you can relate that to things like the rotation period of the comet. So there's a great deal you can do with predictive science like this, a deterministic model. Biology, in general, and humanity for sure, is stochastic on long time scales. So when you think about long time scales, it's the probabilities you think about. How likely is it that one of these bison in this bison herd, this herd of bison in Yellowstone, is likely to wander off in a particular direction? How likely is it that that bison gets taken down by a wolf? How likely is it that there's a wolf in the neighborhood of the bison? All of this comes together. You remember that the wolves were exterminated from Yellowstone some years ago and were only reintroduced a couple of decades ago, 15 or so years ago. So these kinds of changes are significant. The question is, how do you do science in this kind of a context? And that's the problem that we have when you have long time scales. How do you handle the problem when it's probabilistic? So lots of stochasticity, lots of things changing, lots of random issues, and then you're doing things over very long time scales. You can't integrate over those long time scales and get easy results. So let's try to think about this, and I promise you we'll come back to shocks. So let's think about 2 interdependent systems. So I've got 2 things going on, and they're tied together, they're related in some way. So here's a classical idea of 2 interdependent systems. This is the case of 2 interdependent populations, predators and prey, okay? And I want to understand what happens to these populations. So I've got wolves and bison, or wolves and rabbits. Wolves and rabbits are the classical idea here. And by the way, these wolves and rabbits, these wolves and bison, they are subject to a stochastic environment. So around them, the wolves eat the rabbits, but the rabbits have to eat what's growing in the woods, in the forest. And what's growing in the forest changes depending on the climate. And did we have a dry year? Did we have 3 dry years in a row? All of that changes the environment, right? So that's the situation we're in. We're trying to understand that and build a model for that. Here's one way to do it. This kind of this model, the Lotka-Volterra Dynamics model, is sort of a darling of this community right now. And it's a very simple model. I know this is the last class, and I'm going to take it as a given that those of you who are diehards, who stuck with me through all of these classes, you're willing to accept a little bit of mathematics, because mathematics is fun. So let's just look at this. We're trying to calculate what will the population of these two species be, the wolves and the rabbits, how the population is going to change. For any given population, the growth of the population depends on the production rate, how many kids do you have, the annihilation rate, how often do they die, how often do the rabbits die, or how often do they get eaten, and the interaction. So the rabbits die of natural causes, and then the rabbits die because of unnatural causes like wolves, right? That come by and eat. Okay, so you can build equations that describe this kind of a behavior, but the point here is you've got two species, the wolves and the rabbits. The rabbits are the little p, and the wolves are the big P, okay? And the two, you're looking at the growth rate of each of those populations, and those are interacting. So if you look at this equation I've got here, the first equation, the rate of growth, dp dt, the rate of growth of the prey, the rabbits, depends first on how many rabbits do I have. If I've got more rabbits, I can make even more rabbits, right? So this is the growth rate. And then, how often do I get eaten by the wolves? Now, how often I get eaten by the wolves also depends on how many rabbits I've got. If I've got lots of rabbits, the wolves very easily see a rabbit. If the rabbits are rare, it's hard for the wolf to find a rabbit. So you get various functions here that show you the interactions. And you can think of it the same way for the wolves. The rate of growth of the wolves, how easily the wolf population grows, depends on how many wolves you've got. But remember, how many wolves you've got depends on the food for the wolves, and the food for the wolves is the rabbits. So you also have a coupling term from there. If the number of rabbits decays, it's hard for you to grow. Okay, you can solve these two equations. People do that all the time. They do it in all kinds of systems. They do it in biology. They do it in economics, they do it in ecology, they do it in civilization studies, they do it in history, and you get plots like this. So the green curve is the prey, the rabbits. The red curve is the predator, the wolves. And you'll see that there are times when the green curve is going up. So the number of rabbits is multiplying, that's when the wolf population is really low. Then because the number of rabbits is multiplying, the number of wolves begins to climb up. Eventually, there are so many wolves that they begin to eat up all the rabbits, and the rabbit population drops. As soon as the rabbit population drops, the wolves can't find as much food anymore, so the wolf population drops, and you get this nice cyclic behavior. So you can get cycles, okay? So this is one kind of response you will get from these two interacting populations. Now, we said, though, that the prey, the rabbits, have to eat something too. So let's think about that for a minute. So let's think about a single species in its environment. And you can do the same thing if you're talking about bacteria growing in your Petri dish, or for that matter, if you're thinking about a virus propagating through a species, through a population. So here are two possible evolutions. So in this case, it's just one species, and I've replaced the little p with n here. So if all I have is the rate of growth of the population depends on what the population is. So the rate of growth of the rabbits depends on how many rabbits I've got, I get exponential growth. If on the other hand, the fact is I have an environment here in the picture on the right, and the environment says there's only this much food. You keep growing the number of rabbits, at some point the rabbits aren't going to be able to find food, right? So you're going to saturate somewhere. This assumes you don't overshoot. But if you don't overshoot, if everything is in equilibrium, you'll eventually saturate somewhere. This is called logistic growth. So, by the way, this exponential growth idea, this R here, this relates to this infection rate that you might think about for the pandemic problem. How many people are infected by a given individual who is a carrier. You can relate these things. It's a more complicated equation, but the same basic idea. All right, so there's the population, there's the environment. That's the kind of function you get. All right, so we talked about two interacting populations and one population interacting with the environment. Now let's point out that these things can be stochastic. So suddenly the environment might change on you. Something changes and the number of rabbits goes way up, or the number of rabbits goes way down because either they got lots of food or they got no food. What happens to the other population when the first population became unstable? So you think of these, the question is, when you think of these two populations, do you reach a steady state? Are they stable? Are they cycling around some stable curve? Or does one of them become unstable? Part of the question is, when you are perturbed, when you take the environment and provide a shock to it, how will the system respond? Okay? Because you have these interdependent systems, if one system fails, that generates a shock in another system. And you can see things like this. So I need to get across the idea of the carrying capacity. So if I have an environment in which I'm operating, that environment sustains only a certain population. So I'm living in Maryland, I've got the trees around me, the grass around me, that's the only thing I've got. There's a limit to how far I can move out in search of food. So there's only a certain population I can sustain here. That's called the carrying capacity. And you can take this idea across the board. You can think about this in terms of business, but the idea remains the same, it's the carrying capacity. So your local environment sustains a certain population, but the environment is fluctuating. It's changing with time, sometimes stochastically. So you have climate change, you have a major drought, you have a hurricane, the climate changes suddenly. That's one way in which the climate changes, in which the environment changes. A second way is when you use the environment, you might change it. So you decide, well, I've got this human population and I'm going to grow, and my population is growing because I've got food. So I've got a fertile area, I'm going to keep growing food. I've got more people, I'm going to grow more and more food. Eventually the soil says I don't have enough nutrients in the soil for me to grow more food. The yield of your crops decays, you have to move further away, costs you more to move things in. Again, the carrying capacity has changed. So overuse can reduce the carrying capacity. My point here is you have two interdependent systems and you can drive one of those systems into an instability. So one of those systems, which is under normal conditions able to maintain some reasonably steady state, suddenly develops an instability and fails. Let's say you no longer can grow crops. What happens to the dependent population? Will it collapse? That's sort of the key question. Brings up very quickly the question of what's a collapse. I want to talk about that. This is where things get hairy and where scientists and social scientists begin to have difficulty talking to each other. I think everyone agrees that a collapse is a sudden reduction in something, maybe like a jump. So classically, what people think about when they say the collapse of a society is they think of collapse of the population. So you just think of the entire population dropping off a cliff. For human societies, the population may not be a good measure. You could have a lot of people, but they could be living at really low standards of living. So you could have started with something that was a very high standard of living, and then suddenly you collapse into the dark ages, right? So you could also have collapse because that's a collapse of socio-political complexity. So you had a civilization which was complex socially, politically, and that complexity collapses. So that's a possibility. And you may also have cyclic things. So it collapses, then it comes back, it collapses, then it comes back. So most people in this business would say it's not a real collapse unless it's sustained for a significant time and over a significant area. It doesn't mean anything if, this part of Italy, everybody goes away and they go set up in that part of Italy. Or this part of, southwestern Mexico, New Mexico, the Anasazi moved from here to a different place. The society is still vibrant, they've just moved. So it's both area and time. My point here is I gave you equations that changed only with time, but those equations also have to change with space. When you think of human societies, we move around, we interact over distances. People also think about collapse in terms of the breakdown of economic systems. So in fact, this is a paper in ecological economics. I'll show you a couple of others that come out in a minute. Economics is a big user of these kinds of interdependent ideas. Also because predators and prey, a lot of business folks will think of their business in terms of predators and prey. As a customer, by the way, you are the prey. And then of course, one thinks about the breakdown of these interdependent systems. So this is the thing about human society. We build really complicated systems. We build up entire ideologies to be able to support a social system, a political system, a cultural system. If the ideology collapses, all of those systems collapse. And the ideology can collapse simply because you lose faith in it. The picture on the right, this thin solid line, this is data on the number of monuments built by the Maya as a function of time. Actually, the monuments per unit of time here. And you can see at some point that collapses. And people have tried to build models for that, typically using equations just like the one I had a minute ago. So you can think about collapses this way. Whether those models are any good, we can make them fit the data. Are they predictive? We don't know. Here's one example. When I just changed the terms in those equations that I had, we're still thinking wolves and rabbits here. You can see that one of them, the solid black line is the rabbits. At some point, the rabbit population collapses. And that's because this is a case where even a small number of wolves can eat a lot of rabbits. And you set things up so that the rabbits eat really rapidly, the wolves eat really rapidly, and the rabbit population disappears, and then the wolf population disappears. Okay. By the way, this model is also used to look at the exchange rate between different economies. So you can see competition there as well. All right. The last idea I want to talk about is the ideas of overshoot and collapse. So we saw this once before. Let's think about the population size as a function of time, where these solid lines, the dashed lines, are the capacity of your environment. In the dry cycle, you have this red capacity. In a wet cycle, you have this line on the top. In a dry cycle, this is how your population grows and eventually tries to stabilize. In a wet cycle, though, your population says, I've got much more food. It grows rapidly, it reaches here, and then suddenly there's a drought, and you have as many people as this, but you have only as much food as this. And the question is, how does your system respond to that removal of the resource, right? Does your system respond by collapsing, or does your system respond by oscillating down to this? And this is how people who design political systems, political and economic systems, look to control what develops. So just to give you a context for that, this is a paper by Watson in Nature, actually in February 2020, just showing you regions of the world that are under significant ecological pressure. If it's either dark, I don't know what this color is, red, or dark blue, you're under high pressure. If you're green or yellow, you're under low pressure. And you'll see a lot of the Earth is in a high pressure situation. That amounts to saying that those systems are unstable or close to instability. You can think of it going back, way back to our first class. We had the balloon idea. You blow the balloon up, you store a lot of energy in the balloon. Now a single pop then can propagate through the balloon. We are developing the same kinds of systems because of our rate of growth. And of course, people go through great arguments about how this relates to climate change and so forth. I'm not going to get into that. But you can map this out in the data. One of the big strengths we have right now is we can handle the data. So this is the point I want to come back to. We have interconnected systems. This is what defines civilization. And the fact is that an instability in one system can generate a shock in the other. And that shock then propagates to the other system and can lead to the collapse of the second system. This is typically what we think about when we think of most societies. I neglected to show you this, but there was an early case where I talked about the resource stock and the population. That was actually a description of Easter Island. Whether that's a reasonable one, I don't know. That's one that people liked. So I want to close out with this question. I don't have an answer. I'm just going to pose the question. We are good at modeling, or reasonably good now at modeling complex systems. All kinds of complex systems that we can create and test to look at these kinds of problems. We can look at the competition of species in various kinds of controlled environments. We can look at the consequences of resource constraints and overshoots, and how do we manage all of that? We can look at all of that. One thing that we actually model really badly is the influence of technology, how technology acts as a driving force in these systems. And you can see now these strong couplings, right? So we have a technology like social media. You have something that's an instability there, and what does it do in your real world system? So there are lots of interdependencies that we haven't worked out yet. All right, so that's the technical side that I want to talk about. I want to close with some pretty pictures. Let's just close with the art of shocks. I'm going to start by going back to the jump. When the jump is really large, as in the nuclear event, the problem is so intense, the light is so intense, the jump is so large that you don't look carefully. You can't look carefully, right? So this is the origin of the idea that the light's so bright that you have to close your eyes. Now, suppose you kept your eyes open and actually looked at a nuclear blast. And people have done this. What would you see? And I want to show this to you in units of time. And the units of time I'm going to show you are the speed, the time it takes for you to blink your eye. Not the time between blinks of your eye, but the time it takes you to blink. And remember the way the brain is wired, in that blink, you've really tuned the blinking out. You don't notice you're blinking, and so you lose information that's occurring in that blink. Suppose you take pictures of the nuclear blast, and you think one blink after the blast went off. This is what you see. This is one blink, 29 milliseconds after the blast went off. This is the first blink of the blast. The next blink, just 29 milliseconds later, this is what it looks like. And then the next blink, 29 milliseconds later, that's your nuclear blast. And from this, the mushroom cloud develops. You see the structure of the blast? You see the different domains in here. There are different subregions. By the way, this was all taken with a very simple photography system. And there are pictures you can go out and look. Artists who at the time thought that there had to be Satan inside the nuclear blast, right? There had to be the devil in the blast. So there are pictures that you'll see of assorted devils inside these nuclear blasts. But this is what you can actually see during the jump. So even though we see it as a jump, there is detail in the jump, and you can learn a great deal from that. If you get to much simpler scales, this is a kind of art. So this is high-speed photography used as art. This is, I've forgotten the kind of aircraft this is. It's broken the sound barrier, and where it breaks the sound barrier, you get the shock wave. You have a shock wave in a humid atmosphere, and because you've got the humid atmosphere, you get this misty region that you can see. And actually, if you look below on the water, you can see the trail of the shock wave in the water as the aircraft flies. You can look at this also for bullets. So you can see the shock propagate out, you can see the bullet moving, the big shocks moving, and you just do this with colored filters and this technique called Schlieren photography. So you can get really beautiful images using shocks this way. So that's really what I wanted to say. I'm going to close with another poem, also by Omar Khayyam, to try to close, to link these things together. So in those who husbanded the golden grain, and those who flung it to the winds like rain, alike to no such aureate altar turned as buried once, men one dug up again. Think in this battered caravanserai, whose doorways are alternate night and day, for sultan after sultan with his pomp abode his hour or two and went his way. They say the lion and the lizard keep the courts where Jamshid gloried and drank deep. And Bahram, that great hunter, the wild ass stamps over his head, and he lies fast asleep. I sometimes think that never blows so red the rose is where some buried Caesar bled, that every hyacinth the garden wears dropped in its lap from someone's lovely head. So the next time you guys go out and you go on a tour and you go traveling and you go visit the graveyards of former civilizations, take with you the thoughts of shocks and how they propagated through those systems and how the systems chose to respond to those shocks. And to thank all of you for sticking with me through 4 hours of a variety of topics. I hope you see a common thread through all of that. And I hope you're able to take some of this forward into the things that you do and help you structure how you think about the world around you. Thank you very much. Appreciate your time.